Hi there, this episode is an audio rip of a YouTube video. If there are any references to the screen or to the video itself, then be sure to go over to YouTube and actually check out the video, which will be the same title as this podcast. Thanks. Welcome back, and this is chapter 54. This is the Earthing Arrangement Protective Conductor part of part 5. In this chapter, we're going to look at sizing of earthing, sizing of bonding, selection of electrodes, selection of earthing, selection of bonding, and we'll cover the adiabatic equation towards the end. So chapter 54. We've got general, every means of earthing and every protective conductor shall be selected and erected so as to satisfy the requirements of the regulations. The earthing system of an installation may be subdivided, in which case each part thus divided shall comply with the requirements of this chapter. And if there's a lightning protection system, then we'll refer to the standards for lightning protection systems. Earthing arrangements. The earthing arrangements may be used jointly or separately for protective and functional purposes according to the requirements of the installation. The main earthing terminal shall be connected with earth by one of the methods described in Regulations 542.1.2.1 to 542.1.2.3. As appropriate to type of system for which the installation is to form part of and in compliance with Regulations 542.1.3.1 and 542.1.3.2. So 542.1.2, the supply arrangements. This is a little bit of text which just describes these, really. So for a TNS system, the means shall be provided for the main earthing terminal of the installation to be connected to the earth point at the source of energy. Part of the connection may be formed by the distributor's lines and equipment. So there's your TNS there. For a TNCS system where protected multiple earthing is provided, means shall be provided for the main earthing terminal of the installation to be connected by the distributor to the neutral of the source of energy. And that's in there. For a TT or IT system, the main earthing terminal shall be connected via an earthing conductor to an earth electrode complying with 542.2. Okay, installation earthing arrangements. The earthing arrangements shall be such that the values of impedance from the consumer's main earthing terminal to the earth point of the supply for a TN system or to earth for a TT and IT system is in accordance with the protective and functional requirements of the installation and considered to be continuously effective. And earth faults and protective conductor currents which may occur are carried without danger, particularly from thermal, thermomechanical and electromechanical stresses. We'll cover that towards the end of this one. And they're adequately robust or have additional mechanical protection appropriate to the assessed conditions of external influence. There'll be a little mention on that in a minute on the next page on table 54.1, but we'll also look at with like sizing of protective conductors and bonding conductors. We'll be saying if the cables run unsheathed without mechanical protection, so just like a single green yellow cable that's just clipped along, then we'll have to size it to a level for consideration of mechanical strength. Okay, 542.1.3.3, where a number of installations have separate earthing arrangements, any protective conductors common to any of these installations shall either be capable of carrying the maximum fault current likely to flow through them or be earthed within one installation only and insulated from the earthing arrangements of any other installation. In the latter circumstance, if the protective conductor forms part of a cable, the protective conductor shall be earthed only in the installation containing the associated protective device. So if we have a number of buildings and they have separate sources of supply, maybe this building has its own TNS and this building has its own TT system because it's an outbuilding, we either would have them with common electrical systems and they'll be sized to the larger fault current, so it would be the TNS fault current, respectively, because the TT would be a lower current due to the higher impedance. Or we actually insulate them from each other, but we do make sure that the cable going from one to the other, that the protective conductor shall be earthed only in the insulation containing the associated protective device. So the supply end, basically. 542.2 earth electrodes. A good example of that scenario we just mentioned, actually, we're covering caravan parks later on. Electrodes. The design used for and construction of an earth electrode shall be such as to withstand damage and take account of possible increase in resistance due to corrosion. Suitable earth electrodes shall be used. The following types of earth electrode are recognised for the purpose of the regulations. So we have earth rods or pipes, tapes and wires, plates, underground structural metalwork, etc. Okay. It depends on the circumstance, on the the soil's resistivity and the even the conductivity of the soil as to what is the best type of electrode to use, really. 542.2.3, where foundation earth electrodes are installed. This was one of the things they were going to try and introduce for all new builds, but they kind of leant back. But it will probably come in Amendment 1 or 2 more regularly. But where they are installed, the materials and dimensions of the earth electrodes shall be selected to withstand corrosion and to have adequate mechanical strength. Right. The type and embedded depth of an earth electrode shall be such that the soil drying and freezing will not increase its resistance above the required value. With regards to earth electrode testing, it's always a good idea to have them... if you're going to do an earth electrode resistance test when you install it, let's say now this time of year, there's it's we're in a fairly dry spell. It's summertime, but if you were to install an electrode, you'd want to test it again in the polar opposite of the weather conditions, really. So dry, wet, frozen conditions. If you do like regular routine periodic inspections of an installation with an earth electrode, if you were to say I'll come back in 5 years or 12 months or whatever, change it to a month less or a month more, so that as you do some tests that it kind of staggers around the year. Or if you can, move it 6 months, bring it 6 months prior, so that you can test the different seasons with the electrode's resistance. The use as an earth electrode of the lead sheath or other metallic covering of a cable shall be subject to all the following. So adequate precautions will be taken to prevent excessive deterioration by corrosion. The sheath or covering shall be in effective contact with earth. The consent of the owner of the cable shall be obtained, because if they take it away, that's no good, is it? An arrangement shall exist for the owner of the electrical installation to be warned of any proposed change to the cable which might affect its suitability as an earth electrode. This next one, they used to have a lot of questions come out of because of the wording. 542.2.6. A metallic pipe for gases or flammable liquids shall not be used as an earth electrode. The metallic pipe of a water utility supply pipe shall not be used as an earth electrode. Other metallic water supply pipe work shall not be used as an earth electrode unless precautions are taken against its removal and it has been considered for such a use. So they used to throw this around saying, a water utility supply pipe can be used as an earth electrode, and the answer would be in no condition. Followed by a question, when can a water supply pipe be used as an earth electrode? The answer being when precautions are taken against its removal. The key thing is the water pipe a utility pipe? Here's a little illustration of this. So here we have an industry with another building. There's mains power. We've got a sub-main here. And we have our extraneous conductive parts coming into the building. And this is obviously the utility supply pipe, which cannot be used as an earth electrode. And so a separate earth electrode would have to be used. We cannot use the water utility supply pipe. Because if we used it, they could take it away, they could replace part of it, and so its value is obviously not controllable. But then the extraneous conductive part comes into the building, but then it goes off and becomes an extraneous conductive part again, because it goes back underground. So this is something that I mentioned this back in I think chapter 41 when I talked about kitchens and things with cables going underneath. If you put a pipe underground, it becomes extraneous conductive part again. But this obviously, let's say this is the water pipe, this is the stopcock, and then here is a bit of a main feed from it to the outbuilding. This is an extraneous conductive part, but this is under your control, this part of pipework. And if this is under your control, you can utilise it as an earth electrode, as illustrated here. So can a water pipe be used as an earth electrode? The answer is if precautions are taken against its removal. Can a water utility supply pipe be used as an electrode? The answer is no. Okay, we then have earthing conductors, 542.3. Every earthing conductor should comply with section 543, and where PME conditions apply, such as the TNCS system, will meet the requirements of regulation 544.1.1 for the cross-sectional area of the main protective bonding conductor. In addition, when buried in the ground, buried in the ground is what we're looking for here, the earthing conductor shall have a cross-sectional area not less than that stated in table 54.1. For a taped or stripped conductor, the thickness shall be such that it will withstand mechanical damage and corrosion. So we're not talking here about the effectiveness of the earthing conductor for an earth. We're talking about the consideration that taking a earthing conductor and burying it in the ground, it may require sizing to accommodate protection against mechanical damage and protection against corrosion. And that is given in this table. So we have protection against corrosion by a sheath or not protected against corrosion down the left. And we have along the top protection by against mechanical damage or not protected against mechanical damage. So you can see if we had a copper cable, we could be as small as 2.5 if we had both protective measures. If we had neither, 25mm. So quite common, you may get a question along this line of a buried earthing conductor. If the clue is if it's saying buried earthing conductor, come straight here. All right. The connection of an earthing conductor to an earth electrode or other means of earthing shall be soundly made and it will be electrically and mechanically satisfactory and labelled in accordance with regulation 514.13.11, which was the safety electrical connection do not remove tag. It shall be suitably protected against corrosion. Main earthing terminals or bars. In every installation, a main earthing terminal shall be provided to connect the following to the earthing conductor. So we have the CPCs, the circuit protective conductors, which will go to the exposed conductive parts of all of the electrical equipment. The protective bonding conductors. So we have obviously here main protective bonding conductors. What's not illustrated here is the supplementary, but we'll see a little example of that in a second. Functional earthing conductors, and let's remember that functional earthing conductors do not achieve protection, so they cannot be coloured green and yellow. Instead, they are coloured green. And lightning protection if applicable. To facilitate measurement of the resistance of the earthing arrangement, means shall be provided in an accessible position for disconnecting the earthing conductor. Such means may conveniently be combined with the main earthing terminal or bar. Any joint shall be capable of disconnection only by means of a tool. So in your domestics or small installations, you can just get the screwdriver, undo the main earthing terminal and take that out, that's fine. But when you go to the larger installations, switch rooms for example, You'll often notice when you've got all the switchgear in front of you, maybe behind you on the wall or further down in the corner, there'll be a big brass earth bar, and then there'll be all these large earths and bonds, but then there'll be a link, like a bolted link, which then goes to the main earthing conductor. And the idea being, just get a simple spanner or whatever, you undo that link, you swing it off, and you've now removed all of the bonding and all the other earthing from that main earthing conductor, so you can then do a test of the earthing conductor without all the parallels. Just to talk about protective conductors again here in general, we've got the means of earth there. That's the main earthing terminal, so that's the earthing conductor. We have an extraneous conductive part. We have another extraneous conductive part. And so the main protective bonding conductor goes from the main earthing terminal to the extraneous conductive parts. We then have current using equipment here and here. So this conductor is the CPC, circuit protective conductor. And then we have a potential proximity issue with regards to arm's reach. Let's remember that we talked about this, that we only really think about supplementary bonding if we are concerned with the potential value of touch voltage that could occur in a fault condition. And we determine that with regards to the fault current that is achieved, or the fault current that is required to disconnect the protected device for the circuit in question. So the ZS can be referred to determine the earth fault current, and the earth fault current, 50 volts over that, will determine the value of resistance that you then measure between exposed and extraneous conductive parts. This will all help determine whether or not supplementary bonding is needed. Alright. So going to the cross-sectional areas. The cross-sectional area of every protective conductor, other than the protective bonding, so now we're talking about how to determine sizes of earths, not bonds, shall be calculated in accordance with 543.1.3, using that, or selected in accordance with table with regulation 543.1.4, which uses those. Calculation in accordance with 543.1.3 is necessary if the choice of cross-sectional area of the line conductors has been determined by consideration of short circuit current, and if the earth fault current is expected to be less than that short circuit current. If the protective conductor is not an integral part of the cable, and is not formed by a conduit, and is not contained in an enclosure formed by a wiring system, so in other words it's a single green and yellow running on its own accord, then it will be sized 2.5mm if it has mechanical damage protection, or 4mm if not. So that's sizing for mechanical protection there. So those are minimum sizes. It then says 543.1.2, where a protective conductor is common to two or more circuits, its cross-sectional area shall be calculated in accordance with 543.1.3 with the most onerous of the values of fault current and operating time encountered in each of the various circuits. So whichever one is whichever of the two circuits requires the larger earth, that will be a common size for the two cables because it will achieve the highest amount of fault current because of its lowered impedance. Or select in accordance with 543.1.4 so as to correspond with the cross-sectional area of the largest line conductor of the circuit. Similar principle. Cross-sectional area where calculated shall be not less than the value determined by the following formula or shall be obtained by reference to BS 7454. And that's the adiabatic equation. So S is equal to the square root of I squared T over K. This is simply a calculation to determine the minimum size of the protective conductor. So if I just come up with an example. Trying to think of the ones that we used before. Yeah, we did this back in chapter 41, I think it was. With cable sizes, we had IB, IN, IZ, and we came up with a 10mm. We came up with a 10mm. Twin and earth, and we had the scenario here of a 10 kilowatt heater, TNS system, and all that stuff. So that's what we had. Right, so I'm going to cut the video to capture this at the moment. But, so it's S is equal to the square root of I squared T over K. And going from that scenario that we had earlier on, we had a, I don't know which IM we ended up going with. Let's say that we went with, let's say we went with 45. The required current for that type, was it? It was a type C. So that's going to be times 10. It's going to be 450 amp for instantaneous disconnection. It needs instantaneous disconnection. 0.1 to 5. Yeah, so that's it. So it's going to be 450 amp is IF. Now I can confirm that. If I go to the curves in the back. Right, so I'm going to go to the curves in Appendix 3 for the Type C circuit breaker. Alright, that's the Type C circuit breaker. And they haven't got the 45, but they have the 40 and the 50, and the 40 is 400, the 50 is 500, so 45 amp is 450 amp. That's pretty much how that works. So this is what I've got so far. I've got S square of I squared T over K, and I'm calling IF because it's fault current. That's just how my head works. So that's 450 amp. Okay, the T. Now that amount of current, it tells me in this table, will achieve a 0.1 to 5 second disconnection. So I can actually call T 0.1, you know, because it's going to disconnect 0.1. And it tells me, back in 54, that T is the operating time of the protected device corresponding to the fault current. So, right, so the amount of time corresponding to that fault current is 0.1 seconds. So T equals 0.1 seconds. Okay. K is the factor. Now, if we look back on page 197, this was a twin and earth in this scenario that we did. It was a twin and earth, which is 70-degree thermoplastic. Cable. Look at the titles of these tables. 54.2. Cables not incorporated in the cable, not bunched with cables. So that's a single cable on its own. We're not that one. 54.3. A cable bunched with cables. That's probably the one that we want. Table 54.4. It's a sheath of an armour. No, that's crap. 54.5 is ducting or trunking. No. So we want table 54.3 because in a twin and earth, the protective conductor is sandwiched between two live conductors under load. So 70-degree thermoplastic, and we now want copper. We have 115/103 with a star. The star, if you look underneath to the left of it, says above 300 mil. We're not above 300 mil. We're talking here about a 10 mil, and then the corresponding earth for a 10 mil. So we're going to say K is 115, which is quite often what K is for many circumstances. So K equals 115. Alright, so that's what we have. Okay, and I'm just going to calculate that. I'll rewrite it. So S is equal to the square root of 450 squared times 0.1, and it's the square root of the top line. Okay, don't square root the whole sum, and then that's over 115, like that. Now, while I tie this in, just have a think. What if this is a twin and earth cable? Surely the earth has already been determined. You know, 10 mil. What's the size of an earth in 10 mil? Is it 4 mil, 6 mil? Depends what you think. 4 mil is what I have, and I use in the book. So what I'm going to say is, right, well, if this calculation says I need 5 mil, or I need I need 7 mil. Then I'm in trouble. But I want a number under 4 when I do this. So 450 that's the wrong one. 450 squared times 0.1 equals square root over 115. Okay. It was only a very, very small amount of camera. There we go. 1.237. So I'd round that up to a cable size. That's 1.5 mil. I require 1.5 mil. As the minimum required protective conductor. Alright, so obviously the protective conductor coming with that 10 mil, it's going to be fine. Let's adjust it slightly. Let's say that let's pretend the protected device is slightly different. Let's change that protected device to the BS3036. Okay, so, because, why not? Alright, with an MCB, you can see why a lot of circuits kind of get away with design with an MCB, because it works. The device's speedy characteristics and everything just works very well. I'm going to a BS3036. Now, obviously, they don't do a 45, so we'll go with the 40 of that. Well, no, it's an IB of 44, so we're going to have to go... I can't remember. It's 50? Let's have a look. Right, I'm in the curves again. I'm looking at... Right. Oh, they do a 45. Stone me. Okay. So on page 366, back in the curves, you'll see there is a 45 amp. Now here's the question though: what is the required disconnection time? This is where we need to combine our journey so far. We need to now think about what we've done in chapter 41. This is a TN system. It's a final circuit, but it exceeds 32 amp. So a final circuit exceeding 32 amp. It's not a socket outlet circuit. It's a final circuit exceeding 32 amp on a TN system. Yeah, and that was 5 seconds. So we require 5 seconds is our maximum disconnection time. And if we look at 45 amp, it's 145 amps. Okay? Page 366, table or figure 3A2B, 45 amp. Look at the table in the corner. 45 amp, then go along to the 5 second column. Alright? Hopefully I've not lost any of you with that. So, what we're going to change here, we're going to change the current to 145 and the time to 5. Alright, that's what I've done there. Changed the current to 145 amp, and I've changed the time to 5 seconds. I'm just going to put that back in the formula. One, 4, 5 squared times 5 over, it's still 115, equals. So that's the new formula on the bottom there. 145 squared times 5, 145 amp, times 5 seconds over 115. Right, 145, oops. Right. So I now get, camera, 2.819. Okay, so it's over 2.5. There's no 3 mil. I have to round it up to 4 mil. So my minimum protective conductor size, if my protective device is a 3036 with a maximum disconnection time of 5 seconds, which is the requirements of the regulations, changes from a 1.5 to a 4 mil. Okay. It was a 10 mil cable, so we did, so that's fine. But you can just see how it changes, how changing the protected device can suddenly change the adiabatic equation and change the actual circuit's characteristics. Sometimes for the worse, and sometimes for the better. Again, in this case, you can see clearly that a Type C MCB was a lot more effective. But you may also notice, though, that you did require quite a large amount of current on that circuit breaker. 450 amp really was what was required to achieve this connection instantaneously, whilst only 145 amp was needed to achieve the 5 seconds for the 3036. That's an example of calculation. Both, I mean, in the case that we did with the 10mm twin and earth, we did this cable calculation in chapter 41, and we got to the conclusion that with the method of installation and all the factors, the rating factors that we used, we set a 10mm, and we verified volt drop. So we're going 10mm good, volt drop good. We still can't actually use that cable type though until we've done this bit that we've just done, verifying the protective conductor as well. Because if you think about it, the protective conductor, it's an idle cool cable. It's obviously most of the time very dormant. It's not doing much. It's surrounded by two larger cables under load, and they're having a little heating effect. And that cable suddenly may, under an earth fault, just be asked to tolerate all this stress, all this the mechanical pressure of an earth fault. And quite often it can, if it's too small, it can actually during that period of time just break, which is one of the reasons why we're supposed to do pat testing at 25 amp. We're supposed to actually challenge the protective conductor to break with pat testing. So that's what we've done there. We've verified a protective conductor can tolerate the fault condition for the period of time that the fault condition will be there. Right, well that was calculation. The other method was selection. So let's look at selection now. The alternative. We turn the page, so we go to page 198, and it says 543.1.4. Where it's desired not to calculate the minimum cross-sectional area of a protective conductor in accordance with 543.1.3, the cross-sectional area may be determined in accordance with table 54.7. This is an overcompensation table. The calculations that we've just done shows you that you don't need to have a protective conductor the same size. You can have it quite small and you'll achieve sufficient protection. I see a lot of electricians at new installations or existing installations on a TNS system fail because of the sizing of the earth. But if they use the adiabatic and calculate it, it's absolutely fine. So how are we doing this? Okay. Where the application of table 54.7 produces a non-standard size, a conductor having a larger standard cross-sectional area shall be used. So look at the table. It's sized to the line conductor. So we have the first column, cross-sectional area of the line conductor, known as S. So in this example that we've done, S is 10 mil. That was our S. So this says, if our line conductor S is less than or equal to 16 mil, then the minimum cross-sectional area of the corresponding protective conductor, if it's of the same material as the line conductor, which is copper, shall be S. That means if I have a 10 mil, my protective conductor should be 10 mil. So the simple selection procedure here, my twin and earth doesn't work. In fact, if you think about it, twin and earths go up to 16 mil. So any cable that is less than or equal to 16 mil must be the same size as the live conductors. This technically means any time you use a twin and earth with a smaller protective conductor, you should actually be using this method. you should always verify your protective conductors with the adiabatic equation, because this method does not work. This table does not work. Alright. Now, if my protective conductor was a 25mm, sorry, if my line conductor was a 25mm, then you can see it's 16. If my line conductor is 100mm, then it's over 2, so that's 50. Okay, so we just size it accordingly to that. Alright, so we match it all the way up to 16mm, and then we're over that, we are 16mm up to 35mm. If I have anything over 35, then it's half, or the next cable up. It's fairly simple, and in larger installations we wouldn't use it still because it'd be a waste of money. So yeah, that's what I think about that. But it doesn't work with 20 Okay, that's where you have to do that we've just done. And again, I mean, I'll be more than happy to provide some examples and some work examples and some dedicated streams and content to go over these formulas as much as you need to. But that's sizing of protective conductors. Now we have types of protective conductor. It has a protective conductor consists of one of the following: a single core cable, a conductor in a cable, an insulated or bare conductor in a common enclosure with insulated live conductors. Yeah, so like a containment system. And then it says there metal conduits, etc. as well. 543.2.3, a gas pipe, oil pipe, flexible or pliable conduit, support wire or other flexible metallic parts or constructional parts subject to mechanical stresses in normal use will not be selected as a protective conductor. So yeah, flexible conduits, if we use those, we must have a dedicated CPC in there. We can't use metal conduits as the protective conductor of the circuit. The protective conductor of the types described in items 1 to 4 above will be 10mm or less of copper. That's because if we're going to go with aluminium, we start at 16mm due to the fact that we need to size it for strength. Alright. It's fine. 543.2.7. Where the protective conductor is formed by metal conduit, trunking or ducting, or the metal sheath of an armour or cable, the earthen terminal of each accessory shall be connected by a separate protective conductor to an earthen terminal incorporated in the associated box or other enclosure. This is the regulation that answers that question of do you have to earth the back box or not. Back boxes have an earth terminal because if you use the wiring system, a glanded, armoured, or a steel conduit, if you're using the wiring system as your main protective conductor route and not a CPC within the system, then you need to find a way to take that wiring system and bring it to the accessory. Yeah, and that's what that is saying. So, do we earth the back boxes by default? No. We earth the back box to our socket. We earth the socket off the back box if the wiring system of the conduit has taken the back box as part of the wiring system. So we never take an earth from the socket to the back box. If anything, we bring the earth that's arrived at the back box forwards to the socket. 543.2.9. Except where the circuit protective conductor is formed by a metal covering or enclosure containing all of the conductors of the ring, the circuit protective conductor of every ring final circuit shall also be run in the form of a ring having both ends connected to the earthing terminal at the origin of the circuit. So it just lets us know about the ring final arrangement. It's interesting because the ring final circuit is mainly a UK regulation, but that regulation isn't UK specific. So I'm going to do a bit of reading into that because I'm assuming that would be UK specific, that one. Okay. Preservation of electrical continuity. 543.3.201. This is a UK only one. A protective conductor having a cross-sectional area up to and including 6 mil will be protected throughout by covering it of at least equivalent to that provided by installation of a single core non-sheathed cable of appropriate size having a voltage rating of at least 450 to 750 volts. So in other words, if anything is up to and including 6 mil, it can't be bare. It has to be having a green and yellow covering on it. Okay, switching in protective conductors. This is the EU regulation 101. We can go past that. Continuous. Concentric cables. Alright, I want to go to 543.7. Earthly requirements for installations having equipment with high protective conductor current. So .201, .202 and .203. These are all UK specific. So .201. Equipment having a protective conductor current exceeding 3.5 milliamps but not exceeding 10 milliamps. This is a piece of equipment that's between 3.5 to 10. Shall be either permanently connected to the fixed wiring of the installation without the use of a plug and socket outlet, or connected by means of a plug and socket outlet complying with BSCN 60309-2. BSCN 60309-2 is probably what you would consider the old the C-form or the commando type. The difference being that when I look at a 136, one kind of plug and socket, and I go to unplug it, I can potentially, in the insertion and removal, touch an exposed part. I can reach the conductive pin, and if there's any current flowing through to that protective conductor and I'm touching a protective conductor, I can experience some sensation through that. However, if it's the 60309, that's obviously inside the hollow of the socket, and I can't, in the action of removal, make contact with that. .202. Equipment having a protective conductor that exceeds 10 milliamps, this is more, will be permanently wired to the fixed installation. Have a flexible cable and plug to 60309-2 again, in which case the cross-sectional area will be 2.5 mil for plugs at 16 amp and no less than 4 mil for plugs above 16 amp. And the protective conductor will be sized the same as the line conductor, which in a flex it will be anyway. Or 3, you have an earth monitoring system. Okay, so those are stricter requirements. And .203, the wiring of every final circuit and distribution circuit intended to supply one or more items of equipment such that the total protective conductor current is likely to exceed 10 milliamp will have what we call high integrity protective connection and complying with the following. So we'll have a single protective conductor of 10 mil, large mechanical strength there, or a single copper protective conductor having a cross-sectional area of not less than 4 mil complying with the requirements of 543.2 and 543.3, or 2 individual protective conductors to the requirements of 543, which could be of different types. So you can have, for example, a conduit system acting as a return and a single cable in there acting as the route all the way through. So you run the green and yellow cable through, and then when you get to the end, the conduit system returns it. Yes, it's like a loop. Where the 2 individual protective conductors are both incorporated in a single multi-core cable, the total cross-sectional area will be equivalent to 10 mil. Or you have an earth monitoring system again, or you have a double wound transformer. 543.7.1.204, where 2 protective conductors are used in accordance with 543.7.1.203.3, the ends of the protective conductors shall be terminated independently of each other at all the connection points throughout the circuit. So the scenario I just explained, where we keep it as a ring, what we want to do is make sure that those protective conductors don't connect into the same terminal. This is why when you actually look at a socket outlet circuit, and you look at socket outlets, and you look behind them, you'll notice that there are 2 protective conductor terminals, 2 earth terminals. The reason they make those is circuits with high integrity earthing over 10 milliamp will require the protective conductor to be installed in the terminal separately and not in the same terminal. They must be separate. So if one was to come out, the other one was to remain effective. we do need to understand that that goes all the way to the fuse board as well. So in the case of a circuit of high integrity earthing, we'd have to have the protective conductors in 2 terminals. Now, if you remember in section 514, there was a label for this purpose. There was a label that warned electricians that circuits 7 and 9 or 7 and 8 or whatever are both circuits of high integrity earthing, and maybe they are sharing the protective conductors, or maybe this terminal does the protective conductors of 2 and this protective terminal does the other 2. But they must be separate for the circuit concerned. Okay. Socket outlet final circuit, same principle. Okay, so we connect it as a ring. A ring final circuit with a ring protected conductor spurs, if provided, require high integrity protective conductor. Comply with 543.7.1 as we've just gone through. A radial final circuit with a single protective conductor would then have the protective conductor being connected as a ring. So you'd have your radial circuit, then when you get to the end, you take an earth and you come back. So it's a ring for the earth alone. A separate protective conductor being provided at the final socket outlet by a connection to a metal conduit or ducting. Similar principle. So you take the radial protective conductor to the final point, where it then makes contact with a conduit route, which is probably the wiring system for that circuit, to come back. You've created a ring. This other one's quite interesting. Where 2 or more similar radial circuits supply socket outlets in adjacent areas and are fed from the same distribution position, they have identical means of short circuit current and overcurrent protection and circuit protective conductors of the same size, then the second protective conductor may be provided at the final socket outlet on one circuit by connection to the protective conductor of the adjacent circuit. So picture this. Imagine you've got a school computer room and you've got a board that goes to one load of data trunking on one side, another on the other side. They're both, I don't know, let's say they're 25 amp 61009s feeding 10 sockets, but the cumulative value of protected conductor current was to go high. When you get to the end, you can link the protective conductors together, so that whilst you have 2 radials, technically you'd have continuity at the board between the CPC of one circuit and the CPC of the other. Now, this would if this was unlabeled, this would confuse the hell out of an electrician, because he'd have open circuit on line and line and open circuit on neutral because they're in 2 separate breakers, but they'd have continuity between the CPCs. So there must be labelling and warning of that for him. Okay, so that talks about the earthing. Let's talk about bonding briefly. 544. It's very simple. Question is it a PME or not? If it's a PME, we go to the table. If it's not, we go to this regulation 544.1.1. So, TNT systems, TNS systems, except where PME conditions apply, a main protected bonding conductor shall have a cross-sectional area not less than half the cross-sectional area of the earthing conductor of the installation and not less than 6 mil. The cross-sectional area need not exceed 25 mil if the bonding conductor is of copper or cross-sectional area affording equivalent conductance in other metals. So 6 mil or half of the earth. So if my supply main earthing terminal, my main earthing conductor on my TNS system is 10 mil, half of that is 5. No, I'll go 6. 6 is my minimum. If it's 16 mil, well, half of that is 8. The 6 minimum is lower, so I'd have to go from 8 up to 10. I'd go up to 10. Now, if I've got a 25 mil, well, after that, okay, 12 and a half, I'll go up to 16 mil. So you halve it, and then you go up to the next one. Quite simple. We size it to the supply to the main earthing conductor. With PME, however, the main earthing conductor is connected to the neutral, so we size it to the neutral. So, minimum cross-sectional area of the main protected bonding conductor in relation to the pen conductor of the supply. In this case, I don't know, my TNCS system has a 25 mil cable. Okay, 35 mil or less is 10 mil. So you can see with this method, when we use PME, TNCS, we don't go any smaller than 10 mil. Whilst for TNSs and TTs, we can go as small as 6 mil. So, a lot of people go, oh, this, bonding's 10, bonding's 10, bonding's 10. It depends on the earthing system. Alright, so you can't just say, oh, that earth needs to be 10 mil if it's 6 mil. If it's a TNS or a TT, it's fine. 544.1.2, the main protective bonding connection to any extraneous conductive parts such as gas, water, or other metallic pipework or service shall be made as near as practicable to the point of entry of that part into the premises. That's key. I see a lot of local authorities and councils and other places with all the homes that they have, and they'll have these gas meters in little utility cupboards outside, adjacent to the front door, and I'll see some green and yellow cable out there clipping into this unit, or a conduit coming through the wall, and they're exporting the equipotential zone. They're taking it outside of the premises, which is just crap. You shouldn't do that. You should not export your equipotential zone. That's the whole point of it, having an equipotential zone. So it says there, first thing it says is at point of entry to the premises, or the most accessible part after entry to the premises. Where there is a meter, isolation point, or union, the connection shall be made to the consumer's hard metal pipework and before any branch pipework. Where practicable, this shall be made within 600 mil of the meter outlet union or at any point of entry to the building if the meter is external. Couldn't be simpler. If the meter is external, you bond it at the point of entry to the building. Don't take your bond outside. Supplementary bonding to finish. This is just sizing of supplementary bonding. This isn't the question on do we need it or not. That was determined back in chapter 41 when we used Ohm's law. 50 volts over the fault current determined the value of resistance. This is what size would we need if we need it. So, remember that supplementary bonding is to connect exposed to exposed, trunking to exposed metal switch thing, extraneous to extraneous, water pipe to gas pipe, and exposed to extraneous, so switch gear to gas pipe. Okay, so 3 circumstances here, 3 scenarios. The first one, 544.2.1, a supplementary bonding conductor connecting 2 exposed conductive parts, shall have a conductors if sheathed or otherwise provided with mechanical protection. So if they are mechanically protected, there's no need to consider increasing size for that, not less than that of the smaller protective conductor here. So the protective conductor in here and the protective conductors in here, whichever one is the smallest, and I have mechanical protection for this, fine. If I don't have mechanical protection for this, as illustrated here, 4 mil. Okay, 4 mil. The next one, a supplementary bonding conductor connecting an exposed conductive part to an extraneous conductive part shall again, if sheath or otherwise mechanically protected, etc., be not less than half that of the protective conductor connected to the exposed conductive part. If mechanical protection is not achieved, as it isn't here, 4 mil. So 4 mil and 4 mil. Okay. The last one. A supplementary bonding conductor that connects an extraneous to an extraneous. Now this is slightly different. There is no exposed conductive part, so there is no CPC here. There is no existing circuit protective conductor. It's a gas and a water pipe. So what does it say? Well, if we do achieve this mechanical strength sheathing protection, we can go as small as 2.5 mil. In the absence of that, though, guess what? It's also 4 mil. So you can forgive and forget why Sparkies just go, oh, supplementary bonding's 4 mil. It's just easier and saves all the faff. Okay? But if you were to say, oh, you have a switch isolator here with a 10 mil cable and you do have mechanical and sheathing protection to the supplementary bonding, what size should it be minimum? You'd actually say, oh, okay, can't be 4 mil because it's got protection. That's a 10 mil. It says half of that at least. Half of that is 5. No, it goes up to 6. You'd say half of that is 6 mil, but I'll just use 4 because that's okay. It's just easier. So again, it still is easier to use 4. The last little bit there, 544.2.5, just tells you if supplementary bonding is to be applied to a fixed appliance which is supplied via a short flex outlet for an adjacent connection. So you've got like a flex outlet point, and then you've got a flex to like a radiator or something, or a towel rail in a bathroom. Then that little green and yellow cord set, that green and yellow in that cord set there, will achieve supplementary bonding, as you can see, because it's got sheathing protection, it's got mechanical protection, and as these have just been saying, we don't need to size it that much compared to that, so we'll just use it in this case. So don't forget that, because again, I've seen that a lot in the past, where you have a little flex outlet, you've got a little flex coming out, going to a tower rail, and then you've got a green and yellow going with it, which is just, crap. Alright. So to conclude, chapter 54, we've talked about the earthing arrangements, TNS, TNCS, TT systems. We've talked about types of electrodes, plates, wires, tapes, and burying earthing conductors. Table 54.1. Burying earthing conductors. Familiarise yourself with that table. We've then talked about sizing, and we said, okay, well, we had the scenario that we did the previous time in chapter 41's cable calculation, which gave us a 10mm. And we knew that it was a TN system, TNS, and we knew the requirements of the circuit. So we decided to use the adiabatic and calculate two scenarios with two different protective devices. And we figured out that the 10mm was fine because it was a 1.5mm or a 4mm. We also noticed, though, that when we tried the selection method using the tables and the regulations, it doesn't like twin and earth at all. We then looked at the protective conductor currents and the mishmash with those, and then we looked at the bonding at the end, selection of the bonding being determined by the earthing system, whether it be a PME or not. If it's a PME, we size it to the neutral within the conductor. If it's not, we size it to the size of the main earthing conductor. Okay. Run through those scenarios a few times. Familiarise yourself with them. This is all about sizing, selecting of earthing and bonding. The next one, chapter 55, is other equipment, which is going to be a bit of a mix-up of small stuff, really. What fun. See you there.